Greetings! We'll talk about the valorization of rice hull as biomass for ethanol production. To valorize rice hull, we probe the pretreatment aspect as it is one of the most expensive. Cellulosic ethanol making requires pretreatment methods like steam explosion, acid and/or alkaline pretreatment, freeze drying, mulching, and/or a combination of these mouthfuls which are expensive. Agricultural countries like ours have renewable supply of rice hull since rice farming is a supported industry. Experimental paddy like this one provide R&D support for the rice farmers all over the country. This is only a few kilometers from Manila, the city with a charming sunset. The efficiency of cellulose extraction from rice hull feedstock hinge on biomass pretreatment and supply. A typical green countryside like this one is a potential source of rice hulls that can be turned into ethanol. Soon, we'll look into the possibility of feeding bioethanol to spark-ignited engine generators to power farms. It would be a shame if we let the expensive pretreatment be the hindrance to rice hull valorization. There is a way around the expensive pretreatment process that will blow your minds once you realize how easy it is. Once this process is perfected, we won't need to ferment rice only to be triple distilled into fuel. Such is a waste of food. It would have been easier to ferment sucrose-rich stuff like sugarcane extract, but we are vehemently against using food sources. The conversion of cellulose to glucose or saccharification is the preferred route of Verda Materio. The rice hull is cellulose-rich. Otherwise, there's no point valorizing it for green chemicals. Aside from cellulose, it is also rich in silicon dioxide, a compound used as desiccant, insulator, among other things. We heard the grapevine that silicon dioxide is also used in photovoltaic cells, so that's another point for valorization. There is a chemical substance that can dissolve cellulose. We want to know if it can grab the cellulose out of the rice hull. Let's talk about grabbing the cellulose out of the rice hull biomass. This blue gel is cotton dissolving in Schweitzer reagent. Cotton is 99% cellulose. We will try to use Schweitzer reagent to pre-treat rice hull and later convert the extracted cellulose to glucose. This blue liquid in the mason jar is Schweitzer reagent. This is our proposed substitute to expensive pretreatment. This reagent was synthesized by the Swiss chemist Matthias Edward Schweitzer. This can dissolve cellulose. It can easily and readily dissolve cotton, which is 99% cellulose. We want to see for ourselves how wonderful this reagent is. We're excited to see if it can sequester the cellulose from rice hull that they say is between 50 to 55% cellulose. It is worth mentioning that Dr. Schweitzer did not apply for a patent for his reagent. With humble means, Verda Materio determined that alkaline pretreatment is the best suited for the Schweitzer reagent route. We want to confine to simple chemicals because we want this process repeatable and easy to implement. If rice hull does not have lignin, then a single-step treatment with Schweitzer reagent can be applied straight up. The cotton balls don't have lignin, thus the cotton cellulose can be sequestered from the cotton fibers straight away. Rice hull is composed of good percentage of lignin, and there is a need to remove the lignin before saccharification. Of all the techniques, we found out that mild alkaline pretreatment works best for us. It cuts out the lignin upon filtration. Lignin mixed in cellulose can be a great pain. It makes saccharification very difficult, if not impossible. Rice hull is our biomass of choice because it is difficult to pretreat for saccharification. Thus, it will be easier to just burn them in the field and produce greenhouse gases. Rice hull is cellulose rich. If you have a rice farm, you can tap into these resources free of charge. Alpha cellulose are strings of D-glucose in thousands of units per mole of cellulose. A mole of glucose can turn into 2 moles of ethanol. And hopefully cheaper ethanol if the new pretreatment style is perfected. These jars contain copper cellulose complex. Observe that the cotton is fully dissolved. Schweitzer's reagent can potentially reduce the cost of rice hull pretreatment. Our key to rice hull valorization is a copper-based reagent. Its deep blue color is owed to the natural color of copper in a 2+ oxidation state. This change of color is akin to the characteristic of a deep block or transition elements. Iron is a D-block element which turns green when it oxidizes to 2+ state. It turns orange to red upon further oxidation. Manganese is another D-block metal. It turns pink upon oxidation. Its crystals are beautiful purple. Unlike the rare earths neodymium, gallium, germanium, and platinum, copper is readily available and even available as scrap. Schweitzer's reagent can even be prepared from raw junk copper. Notice the moist due to endothermic reaction. Using only a jar and a piece of disposable fork, we neutralized and coagulated the cotton cellulose. This is the filtration of raw cellulose from cotton after the neutralization of the copper cellulose complex. The cotton cellulose will turn white after washing. As for the rice hull cellulose, the liquor turned green, but without lignin, the cellulose is light brown. Next is saccharification. Our enzyme is our lucky find. We have been looking for an enzyme for so long. The enzyme is the key to our successful conversion to glucose, or saccharification. One of our setups is the unbuffered cotton cellulose. It didn't convert to glucose. Lesson learned, buffer solution is important. One of our setups is the buffered cotton. It showed 3% bricks in the refractometer. Our untreated and buffered rice hull setup is between 2 to 3% bricks in the refractometer. This is rife with lignin. The treated and buffered rice hull setup is also between 2 to 3% bricks in the refractometer. This was treated to remove the lignin. We excluded the unbuffered cotton for the next test since the reading is too low in the refractometer. The untreated rice hull, the one with lignin, failed the glucometer test, even if it has results in the refractometer. The buffered cotton showed 5.6 millimoles per liter glucose converted. The treated and buffered rice hull had 1.8 millimoles per liter glucose converted from treated rice hull cellulose. Crude as it is, we can claim that the combination of alkaline treatment and Schweitzer's reagent produced cellulose. Verda Materio, at least qualitatively, proved the usefulness of Schweitzer's reagent in producing cellulosic ethanol. But we're not going to attempt to write the stoichiometry of this saccharification reaction we made. Cellulose is a polymer, and we don't know how many glucose units our product has precisely. But we will not stop here. Our experiment is crude and inaccurate. It is lousy qualitative at best, similar to dipstick approach. To ask how many glucose units our cellulose have is like asking how heavy a random piece of rock is. Soon, We will perform the quantitative test according to standard references. Then, we'll define the stoichiometry relevant to this. Then, we'll be able to consider the costing of turning rice hull into a clean burning ethanol. Yes, it spews out carbon dioxide upon burning, but less than what is given off by fossil fuels. It is less efficient than fossil fuels, but the voltage produced here is from green source. The carbon dioxide that becomes part of the plants during photosynthesis gives off oxygen and water. Notice these beautiful water globules on rice seedlings in the morning. These water droplets are products of photosynthesis, and hopefully in a carbon neutral manner.